All right, so this is going to be our warm-up problem for doing another molar mass type problem. Molar mass of gases. So let's read the problem. A lot of this chapter is making sure you can identify like what measurements are given, like which one is pressure, which one is temperature. Temperature is pretty easy, but some of the other units aren't as familiar. So like 250 milliliters, this is a unit for volume. So we have a volume. They're telling you it's a noble gas, meaning it is either helium, neon, argon, krypton, xenon, or radon. So we know it has to be one of those gases in the family. And then 88.1 kilopascals. Kilopascals measures pressure. So we have a pressure. And then obviously 7 degrees Celsius is temperature. So we have a temperature. And I also give you mass. Mass measured in grams. And I ask for molar mass. So if you remember, there are two ways to do this. All right. I will go over both ways, but again, how you do it on the test is up to you. It's going to be whatever you feel more comfortable with. Let's see. Why is this not combined gas law? Like P1 V1 over P1 V1 over T1 equals P2 V2 over T2. Well, in the combined gas law, that was the one we first learned in this chapter, there's like you either have to have two pressures or two volumes or two temperatures, and we definitely do not have any of that. So this is going to be our ideal gas law. So what is our ideal gas law? Our ideal gas law is PV equals nRT. And then the new equation we learned yesterday that you do not have to memorize, but you have to know how to use it, that the number of moles, N, equals mass divided by molar mass. So in case they want to know molar mass, like they do in this problem, you can take now this thing. So both of these equations will be given on your test and replace the moles with it. So now instead of writing the Pervner equation, the ideal gas law like this, you write it like this. PV equals mass over molar mass, RT. Okay, now they ask for molar mass in this problem. So molar mass is the big capital M. And right now it's in a denominator. So if you want to solve for it, you cannot leave it in the denominator. So I'm going to multiply both sides by molar mass. Sorry about this. Molar mass. Now that gets rid of molar mass over here, right? They cancel out. That was the point. And now my molar mass is up top, which is good. So now I need to get the molar mass by itself. So I divide both sides by PV. So this whole thing divided by PV. And now molar mass is by itself. This is the equation for molar mass with mass in it. At this point, we plug and chug. You have mass, you have temperature, you have pressure, you have volume, and you can look up the R constants. They will always be given. You don't need to memorize them. So let's go back to the problem and kind of find out what some of our numbers are. So the mass is 0.378 grams, okay? Now, the R constant is going to be based on your unit of pressure. So you want to use the R constant that matches the kilopascals. Again, if you reference back, you'll find that that number is 8.314, okay? Again, you don't have to memorize it. It will be given. You just have to know how to use it. So 0.378 grams, right? Was that right? There's my mass, M. R is 8.314 liter kilopascal over mole Kelvin. Those are all the units. And T is temperature in Kelvin. Well, the temperature they gave you was 7. So you take 273, this is the conversion factor, and you add the 7, and that is your temperature. So 280 Kelvin. Divided by, the pressure was it 88.1? 88.1 kilopascals. And the volume was 250 milliliters. Now, you cannot leave the 250 in milliliters. If you don't know this, there are 1,000 milliliters in 1 liter. So that's 0.250 liters. The reason that is because the R constant volume in it is liters. It's not in milliliters. So if in order for the units to cancel out, you have to be in liters. So let's look at the units. So look at kilopascals on the top, kilopascals on the bottom. Liters on the top, liters on the bottom. Kelvin on the top, Kelvin down here on the bottom of this. Grams divided by moles. That's what molar mass is. Grams divided by moles. So I want to give you a second, please, to punch all of these numbers into your calculator.
You got like 400 per minute. I'll just double check it.
So if you got 400, that's probably a calculator issue. It's definitely 40. So because they say 40, and they also tell you it's a noble gas, you can identify who it is. So basically you go to your periodic table, you find your last column, right? That's your noble gas family, and you go which noble gas has a molar mass closest to 40. So let me pull up my P table.
Does 280 have a decimal?
Yeah, 280 is, well, I guess technically it doesn't have a decimal, but it goes to the ones place.
Yeah, like I calculated again, yeah, like 400.
Okay, well, I mean, what did you put for the volume of the gas? 0.250, right?
Yep, 0.250.
I would just try in your calculator again. It's for sure 40.
Okay, wait.
So you'll see that 40 grams per mole is the closest to argon. On this periodic table, it says argon is 39.95 grams per mole, which is really close to 40. So based on this information, the noble gas is likely to be argon.
What does that say next to the A? Just want to know.
This is 88.1. 8.314 to 80 divided by 88.1 and 0.250. So this is one way to do this type of problem. The other way that will still get us the right answer is going to go like this. So again, we have two equations. PV equals nRT. And then we know that moles is mass over molar mass, which really just means molar mass is mass over mole, right? Just one. This is just a rearrangement of the equation, right? So if you have mass and you have moles, you could find molar mass. Mass is measured in grams and moles is measured in moles. Well, we're kind of halfway there. By half, I mean we need two things, mass and moles. I have mass. I gave you it. It's 0.378 grams. So I already have this top part. So if I could figure out moles, I could take my grams and divide by moles, and I would get molar mass. Well, what's nice is that Pevner has moles in it, right? So instead of taking this guy and plugging it in here, I could just use plain old Pevner to solve for moles because I have pressure and volume, and you always have R and temperature. So I could solve for moles, put it in here, and then do this math. That's an alternate method to do it. So if I rearrange this, it's PV divided by RT to get moles, right? You divide both sides by RT to isolate the moles. So now we plug in. It was 88.1 kilopascals. The volume is 0.250 liters. It has to be in liters, not milliliters. The R constant was 8.314 liter kilopascal over mole Kelvin, and the temperature was 280 Kelvin. So look at the units. The kilopascals cancel, the liters cancel, the Kelvin cancel, and you're left with moles, which is what I'm trying to find. So you calculate this number out. I'll give you a second. Let's see. When you have two things in the denominator, it's helpful to hit your divide button twice. So what I mean by that is 88.1 times 0.25, then hit your divide button, 8.314, and then hit your divide button again because both of those are in the bottom. Sometimes when you use parentheses, it can mess up your two numbers in the denominator. So the number of moles I got was 0.00946 something 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 something. So you take 0.378, you divide by the moles, and you get 39.95, which really is 40, right? Okay, so it's the same number. This is just an alternate method. So you do whichever way you feel comfortable with. So just like the Pervnert equation that we did before, right? So we did we said, okay, ideal gas law is PV equals nRT. And the new thing we said was moles is mass over molar mass. That's how you get to moles. Okay. We also know that density is mass over volume. That's the equation for density. So really, you can write this expression with density in it. And here's how it works. In order to have density, you have to have mass divided by volume. So I'm going to replace the moles so that I have mass in my ideal gas law. So it goes like this. PV equals mass over molar mass, RT. This is what we've been doing. Now, I'm going to rearrange this so I get mass divided by volume by itself, because that is what density is. So I'm going to put molar mass up here. Multiply both sides by molar mass, right? That will get rid of the molar mass. Okay. Now, I'm going to divide by volume. Mass over volume, right? And the RT is technically over volume also. Okay. And then you should notice this is density. Mass divided by volume is density. So how do I get that by itself? I divide both sides by RT. So again, this is just different algebraic manipulations of the ideal gas law. So density equals molar mass times pressure divided by R divided by T. And I'll do this a bunch of times, well, two or three times with you today to show you how to convert this ideal gas law. So basically, we turn the ideal gas law into a density gas law, a gas law that has density in it, just by using these manipulations. So it says, what is the density in grams per liter? Now, we haven't really talked about density like that. Like, the density we've done so far in here has been grams per milliliter, grams per centimeter cubed. This is usually for liquids. This is usually for solids. This mass over volume is for gases. Anybody want to guess why the bottom unit is so big? Like, because this liter is really big compared to like a milliliter or centimeter cubed. And the reason it is because gases take up a ton of space. So you have a bigger volume unit when it comes to gases because they occupy so much space, okay? So it says, what is the density? Density is D, right? Which is the same thing as mass over volume. And I give you a mass of Cl2, and I give you a pressure, and I give you a temperature. You go, okay. There's two ways to do this problem in this one. So let's see. Here's our ideal gas law. And here's our moles equation. Both of these will be given to you on the test. So let's see. I have pressure. I have temperature right here. You always have R. Now, I don't exactly have moles. I guess I could get moles, and then I could find volume, and then I could take mass and divide by volume. That's one way. In fact, let's do it that way first. I have mass right here. It's 15.6 grams. Mass divided by volume. I don't have the volume yet, but I have enough to get me to the volume. Because even though I have grams of chlorine, you should be able to turn grams into moles of chlorine using the periodic table. That's what we've done a bunch of times this year. So if I rearrange to solve for volume, that means I divide both sides by P, right, to get volume by itself. So let's see, how do I turn grams into moles? Well, 15.6 grams of Cl2. The grams go on the bottom, 1 mole goes on the top. This is molar mass. Mass divided by molar mass gets us moles. Mass divided by molar mass gets us moles. So chlorine. Chlorine is 35.45 on the periodic table. 35.45, but there's two of them. So it's 35.45 times 2, so it's 70.9 for the chlorine. 70.9, because it's diatomic. So 15.6 divided by 70.9 will give you your moles of chlorine instead of your grams. So that ends up being like 0.22. Basically, it's 0.2200282 something, something, something. So my moles are done. So V equals, all right, my moles come out to be 0.22, basically, moles. That's N. What is R? Well, you want to pick the R constant based on pressure. The pressure I used was atmospheres. ATM means atmospheres. And the R constant that goes with atmospheres that you don't have to memorize, you just have to know how to use, is 0.082. Liters times atmospheres over mole times Kelvin. T is temperature in Kelvin. Oh, they finally gave us one in Kelvin, so I can just plug that in. I don't have to do any converting. It's already in Kelvin. Awesome. Divided by pressure is 1, so that's kind of boring. It's not going to do anything to the number, but 1 atmosphere. So let's look at our units. Moles cancel, Kelvin cancel, atmosphere cancel, and we're left with liters. Is that a good unit for a volume? Yes. So you take 0.22, you multiply 0.0821, you multiply again by 298, and then you divide by 1, which does nothing to your number. And that gives us my volume in liters. So that gives me my bottom part down here. It looks like it's, I'm going to write a bunch of numbers because I'm not finished. Let's try to change the color. 5.38311. Keep the whole number in your calculator, and you take 15.6 grams, divide by liters, mass divided by volume, and you should get, I'm going to write it up here, 897, so that's 90 grams per liter is the density of chlorine gas. So I'll give you a second to work out those calculations, and then I will show you the other way. You know what? I lied. I'm just going to show you one way to do this one so I don't confuse you. So you have a sample of uranium hexafluoride, okay? If you didn't know, this is like a super heavy gas. Uranium is super heavy. And so I have moles. So I have N, and I know who the gas is, so I can turn this into grams if I need to, right? If I need to, we'll see. And I give you a pressure. And I give you, so this is P. And I give you a temperature. Now it's in Celsius, so we're going to have to convert that to Kelvin. In fact, let's just do that now. 100 plus 273 is 373 Kelvin. Because we can't use Celsius, we can only use Kelvin, and we can only use liters. Those are the two units you have to be careful with for the ideal gas law. And I want to know the density. Okay, well, density is mass divided by volume. So let's see if we have enough information. Right. Density is mass divided by volume. So we know that. And we also know we're dealing with a gas. And so ideal gas law, if we're dealing with gases, is probably helpful. Now, I gave you moles, but I did not give you grams. Can you turn moles into grams to get mass? Sure. You could get mass very easily. You turn moles into grams. Could I get volume using the ideal gas law? PV equals nRT. Well, I don't know. Do I have enough? So if I want to get volume, I better have all of the other variables. So do I have pressure? Yes. Do I have moles? Yes. Do I have the R constant? You will always have it because you can look it up. Do I have T? Yes. Okay, so I have a way to do this. So the first thing we're going to want to do is turn 1 mole of UF6 into grams. So this is going to be pretty easy. You go from moles to grams using the periodic table. So you take a uranium and 6 fluorines and you add them together. So fluorine is 19 times 6 because there's 6 of them. Plus uranium is all the way down here. It's 238.03. This is a huge, or this is a heavy molecule. It is 352.03 grams per mole. 352. Now, the thing is we only have 1 mole of it, so 1 times this number is just 352.03 grams. So there's my mass. Now I need my liters, grams per liter, mass over volume. That's what I don't know right now. So I'm going to use PervNERT to get me to liters, liters, which is volume. PV equals nRT. So how do I get volume? I divide both sides by pressure. That's how I get volume by itself. So now, what was my moles from the problem? Well, it was 1. That's N. You can go look up the gas law constant R for atmospheres because that's what they gave pressure in, right? It's 0.0821 liter times atmosphere over mole times Kelvin. And then T is temperature in Kelvin, which was it 373, right? 100 Celsius is 373 Kelvin. And the pressure was I already forgot, 9 something, 974. So moles cancel, Kelvin cancel, atmosphere cancel, and now I will have my volume part of density. So density has two parts, mass divided by volume. So calculate this out. 1 times 0.0821 times 373 times, divided by 0.974. I will wait until you tell me what you get for volume. So again, we use the ideal gas law to find the volume portion of density. Density has two parts. It has mass and it has volume. Mass divided by volume. So we found the mass, we used perv-nert to find the volume, and then we divide the two numbers. Mass divided by volume is density, and it comes out to be 11.2 grams per liter of uranium hexafluoride. All right. I actually think that I'm not going to do stoichiometry in this session. So give me 1 second.